All right, welcome to Honors PreCal. So this would be the first video that I am going to be doing. This is Miss Kosh. You'll find in a lot of my answer keys, I write my name on every page, just so you know. I get the credit and the blame. So when I make mistakes, I apologize, but I'm good, but I'm not perfect, so here we go. On this one, we're beginning with functions. I expect this is a bit of a review for you, but I'm going to teach it like you've never seen it. I just might go a little bit faster. So we talk about the difference between a relation and a function. A relation just can have, well, if I had a circle, there is some sort of relationship between the x and the y values, but it's not, it's a relation, but it's not a function. So it has two quantities, the x and the y are related to each other. There's some sort of rule there, but it's not, what happens with a function is that each element in the x has exactly one element in the y. Okay, it doesn't necessarily go the opposite way. A one-to-one function would go the opposite way, where every element in the y also has one in the x, but we'll kind of get into that a little bit more as we go. The domain are the x values, the range are your set of y values. A piecewise function is a function defined by two or more equations. So we're going to, as we keep going, like this number 4 here and number 5, those are piecewise functions for us. Okay, so in your own words, what's a function? What is not a function? A function is anything for every x, there's exactly one y. And what is not a function? Anything that has multiple y's for the same x. So the easiest thing to remember is that if it does it pass the vertical line test. So if I have this, can I draw vertical lines and always hit exactly one spot? Well, yes. Okay, so this would be a function. If I have something like that circle we saw a second ago, when I go to do the vertical line test, I'm hitting it in two different places. Okay, so that would not be a function. Okay, so that should be mostly a review for you. So the next thing, in your own words, when is a function defined? Well, there's two things, I lied. When is a function undefined? There's two things that you can't do. And one of them involves my favorite math joke of all times. So I don't know, it's the very first video. I don't know that you're really ready for my very favorite math joke of all times, but here you go. My favorite math joke, well, first of all, if you were in my classroom right now, I would say everybody knows who Chuck Norris is, right? Okay, well, pause the video if you don't know who Chuck Norris is. Go Google him, then Google Chuck Norris school appropriate jokes and get the idea of, it's all sorts of things like Chuck Norris doesn't do push-ups, he pushes the earth down. And that sort of thing. So anyway, go Google him if I'm not making any sense to you. Okay, so my favorite math joke of all time is that Chuck Norris can divide by 0. My second, here's where you laugh, okay. My second favorite math joke is that Chuck Norris counted to infinity twice. Oh, this is just not as much fun without you in my room. I miss you guys. Okay, so I hope you're laughing. If not, it's going to be a long year. Okay, so the first thing, when is a function undefined? And I'm going to write down, well, divide by 0, because you can't divide by 0. Anytime you end up with a 0 in the denominator, you got a problem. So that's where I refer back to my Chuck Norris joke, and I have a poster. When you come to my classroom, you'll see my Chuck Norris poster. It was made by some IB kids a few years ago. The other thing that we can't do, number 2, the other thing that we can't do is we can't take the square root of a negative. If you do, you leave the real world. Okay, so like if I said the square root of -4, that's equal, you may remember from Algebra 2, up to 2i, but that's not, this, ladies and gentlemen, is non-real. Okay, so what we're trying to do here, and you'll see as we start looking at these examples, is we want to make sure that anything we plug in for x gives us a real value for y, okay? And so if I had a negative underneath the square root sign, I have left the real world and I have entered the imaginary values. Okay, so let's look at the first one. If I look at this first one, there's nothing wrong with the numerator, Okay, I'm not trying to divide by 0, and there's no square roots in the numerator. So that part right there doesn't matter in the slightest. The second thing here is, well, the other part is that cannot equal 0. That's that little rule 1. So the square root of x minus 3 had better not equal 0, which means that I can't take, well, the square root of 0 is 0. So I can't let that means that x minus 3 cannot equal 0, which means that x cannot equal 3. Okay, this may not, that fits the first rule. Let me show you, the second rule is that I can't take the square root of negative. So that means that this x minus 3 has to be positive. It can't be, well, it could be 0. So it has to be greater than or equal to 0. So this is x minus 3, well, hang on, I don't need to write x minus 3 again. That means I add 3 to both sides, that x is greater than or equal to 3. But when I put these two together, you see what I'm talking about? These two together, what I'm really going to end up with is that x has to be greater than 3. So this is one of my, one way to write the answer. The other, hang on, I could say it in interval notation, which would be from 3 to infinity. Or I could say it in set notation. And that's where you use the set brackets here, and you say x, it's the set, x, such that I use a colon, but you can also use a little straight line. I'll write that in a second. Such that x is greater than 3 is how you could write that in set notation. The other way that sometimes you see x such that x is greater than 3. Both of those are correct for such that I tend to use this, and I tend to use that. So that's the very first, that's the first answer to that problem, or that's the answer to the first problem. Continuing on, let's pick a new color. Continuing on right here, what we need here, we need to consider rule number 1. Oh, actually, let me come back to that first one. What I would do is I wouldn't necessarily apply both of these once I know what I'm doing, if that makes sense. What I would do is I would say, oh, this is in the denominator, and it's got a square root. So that means that this x minus 3 has to be greater than 0. If it's equal to 0, then I'm dividing by 0. I'm not Chuck Norris. I can't divide by 0. If it's, but it can't be, yeah, okay, that's what I meant. So then we would just add 3, and we would just say that x is equal to 3. And that's how I would, I don't necessarily consider those two rules separately. I am, but I'm not. Okay, hopefully that made sense. Let's look at the next one. On this one, what we need to do is there are no square roots, so we don't need to consider rule 2. What we need to look at is to say, okay, well, x squared plus 2 cannot equal 0. Well, okay, so that means that x squared cannot equal negative 2. Well, the good news is that whatever real number I plug in for x will always give me a positive number or 0. Okay, it can never give me a negative. Another way to think of this is this means x is equal to, x can't be equal to plus or minus the square root of negative 2. Well, this is non-real. And so if I'm graphing this over the real numbers, and all I can do is plug in real numbers, well, in for this x and that x. Okay, sorry, that got messy. If all I can do is plug in real numbers, well, then I'm always going to get something that works. Okay, if you think about it, let's use a different color. I don't know, that one. If I were to say, okay, well, f of 1 would be equal to 1 squared is 1 plus 2. So that would be equal to 1/3. If I were to say f of 0, that would be equal to, well, that's 0. That's 1/2. If I were to say f of negative 1, notice that negative 1 gets squared. So negative 1 gets squared. A negative times a negative is a positive 1. Plus 2 is 3. That's in the denominator, and there we go. So no matter what I plug in, I'm always going to be able to get a real, I'm always going to not get 0 in the bottom. Anyway, I said it. It's not sophisticated, but there we go. Okay, so this one, this function, has a domain from negative infinity to positive infinity. Those of you that are going to head to my IB class, they write this in a weird way. They go like this. So it's those brackets turned around. Okay, that's neither here nor there. I think it's cool, but whatever. Okay, next point, we asked us for the domain of this. So here, what I need to do first is I need to figure out when can the denominator equal 0. Notice once again, there are no, there's no square roots in there, so I'm not worried about this. So I'm just worried about that part right there. Okay, so new color. There we go. Well, okay. So when I look at this, I'm going to say, okay, well, how do I get the denominator to equal 0? Well, I have to factor. This becomes x. So something like this, I'm hoping that you're good at factoring. One of those is going to be positive when there's a 3 times a 1, so it's a positive 3 and a negative 1. Which means that if x plus 3 equals 0, then the whole denominator would go to 0 and we'd have a problem. So I could say that x plus 3 can't equal 0. So therefore, x cannot equal negative 3. I can say x, oh, my bad. I jumped ahead. I do go fast sometimes. Okay, so x minus 1 can't equal 0, which means that x cannot equal positive 1. So on this one, you could tell me either it's from negative infinity to negative 3, pick it up again and go from negative 3 to 1, then pick it up again and go from 1 to infinity. That's that interval notation. Or you can tell me in set notation, it's the set x, such that x is not equal to negative 3 or 1. I'm happy with either one. Okay, so that's going to be the first video, and I will come back and continue with the rest. We'll see how many videos that I am needing to make.